Okay, so you guys said that you wanted to talk about vectors, since we hadn't really talked about vectors yet. So we've talked about parametric equations, we've talked about polar equations. Here in Barron's book, we talk about vectors, so motion along a curve. So there's a couple things in here that are pretty important for you to understand just the concept of a vector. So I'll go ahead and highlight some of the things that you can think of when you think of vectors. So P is called the position vector. So just like, here I'll make that highlighter a little smaller so we can get more defined. There we go. P is called the position vector. So just like we talked about in calculus AB, you had your position function, which was usually represented by S of t. And the derivative of the position function was the velocity function. The derivative of the velocity function was the acceleration function. That's kind of what we're talking about when we talk about vectors. And since we're talking about them parametrically, you can see up here that it talks about them in terms of p of x, or p of t, I'm sorry, being x of t comma y of t. So vectors have you guys taken physics?
Yeah.
All right, so vectors, did you learn about vectors in physics?
Yeah.
Okay, have a horizontal component and a vertical component. And so that helps to make up whatever angle or slope that they have. So the horizontal component is obviously the x component, the vertical component is the y component. And so together they tell you kind of how far it goes as well as what direction it's going in. Because they have a direction and a magnitude. That's what a vector is. So it says the set of position vectors for all domain is called the vector function, and it's symbolized, I'm not sure how the AP test symbolizes it, but I know it can either be a bold letter R or an R with a little arrow over the top of it. This was saying that in print it's easier to make it bold, and in handwriting it's easier to do the R with the arrow over the top, since it's obviously difficult to make something bold when you're writing it by hand. So the most probably in hand that you'll see it written as is more like this one, so I'll highlight it in pink. It's this R of t with an arrow over the top equaling x comma y. And notice that it has those like random wide kind of like caret brackets around it. So that's vector notation. Can you guys read that, by the way, up there?
Yeah.
Okay. So that's the position function, is that you'll have some x comma y in those brackets like that. And so for the velocity vector, remember the position function is notated by r.
Why do you say the brackets were like that?
Why did I say that they're like that? Because that's just the notation for a vector. So anytime you see something in calculus that has those big wide caret brackets, that's talking about a vector. So you'll notice that if you take the derivative of each one individually, so for example, the derivative of x would be this dx down here, the derivative of y would be this dy down here. So you take their derivatives individually with respect to t, and that gives you what the velocity vector is. So dx dt and dy dt are the two components of the velocity vector. So position vector tells you, and just if I can kind of make some room up here, so I'll white out some of the space so I can kind of draw it so we can get an idea of what we're talking about so far. So let's say that we have these parametric equations. Let's say they define an ellipse that looks like this. All right, so at any time t you can have different positions. Hi.
Hi, Michael. I freaking called you to come open the door.
Michael.
Oh,
So
I have my phone on silent.
I got too much messages.
I doesn't even vibrate.
All right, so you, as t increases, so as time increases, you kind of go around the ellipse, right? So let's say that at time t equals 0, you're right here, and at time t equals whatever, you're right here, and time t equals whatever, you're right here. So that's your position as you're going around. So the position function, the r of t, tells you it's essentially a vector that goes like that, and it says it has an arrow on the end, because all vectors have arrows on the end because they have direction with them. But it's essentially a vector that says at time t equals 0, that's where you are, is way over there. Or at time t equals 1 or whatever, you're up here. Or time t equals pi over whatever, you're up there. All right, so the position vector originates at the origin and goes out to the graph to tell you where you are at certain times. All right, and you'll see like a line, that's what you have to actually draw in the line. If they ask you to draw the vector, you'd actually have to draw in the line to show that. The velocity vector, so this derivative, dx dt, dy dt, it's always going to be tangent to the curve at the point that you're looking at. So let's say at t equals 1, all right, we're going to be looking at a velocity vector. It depends if you're going counterclockwise around or clockwise to determine the direction, but essentially the velocity vector will be tangent and it'll look something like that. All right, or if I put it right here, it would be tangent and look something like that.
It's not from like both sides.
It doesn't go both ways because it has a direction. So like, for example, if I was going counterclockwise, it would look like this. If I was going clockwise, it would go the other way and it would look like that.
Okay.
You know what? And to figure out how long the line needs to be that you're drawing, you need to determine what the magnitude of the velocity is. So all that this is telling me is the direction. To figure out how long it needs to be would be the magnitude. And we'll talk about that in just a minute. So if I can erase all of this, and I'll show you the acceleration in just a minute. But so this one is important for the velocity vector. So the velocity would be dx dt dy dt in those brackets, those open caret brackets like you see. You'll also see it, it's really small, so I'll write it a little bit bigger, but you'll also see like dx dt written as v of x, or v sub x I should say, that's a little v sub x, that little arrow I pointed to. And then dy dt you'll often see is written as v sub y. So anytime you see v sub x, know that that's the velocity in the x direction, and anytime you see v sub y, that's the velocity in the y direction.
Is that a typo in the book? I don't know.
Where?
It says or b with like the arrow on top and then t. And then it says dx over dy. Why is it over dy?
That might be a typo, because that does not seem right to me.
Yeah.
Yeah, I think that's probably a typo. Let me make sure that over here. Yeah, that's a typo. Okay, good. So those are the velocity components respectively. All right, so they're derivatives respectively of dx dt and dy dt. It says that those are the components for the horizontal and vertical directions. To actually find the slope of the line, to figure out what the slope is, you just divide their horizontal and vertical components. So this one down here, you divide dy dt by dx dt and you get the slope dy dx. So if you ever had a question that said like find the slope of the velocity vector, you know, this would be dy dx, or dy dt over dx dt would be the slope of the velocity vector. So that tells you kind of like which direction it goes in, like I told you earlier, or like we talked about earlier, I should say. And then to determine how far it goes, so the length of the vector that you actually draw comes from this one down here. What does that look like to you guys? The square root of, yeah, it should look kind of like a squared plus b squared equals c squared. It's just that they square rooted the c squared to make the square root go on the other side. But I'll show you, I'll draw a picture over here to show you, while you're writing that down, to show you where that comes from. So what I just drew over there is a little right triangle coming off of the velocity vector that shows you that the horizontal and vertical components together make up the magnitude of the velocity. So, you know, if you square x dx dt and you square dy dt and you add them together and you take the square root of that, that'll be the length of this line here. So it'll tell you how long that is. So yeah, that's where we get that formula down below for the magnitude of the velocity is essentially from the Pythagorean theorem. So that's where we found that one out. All right, let's position this over here. So this is kind of like the end of the notes section for velocity. I'm sorry, for vectors. So we'll do some examples after this, but you have to know these couple formulas as well. So it says, thus, if the vector v is drawn initiating at P, so remember that P is the point on the graph, r is the vector going from the origin to the graph, p is the actual point on the graph. So they're saying if the vector v is drawn initiating at p, so starting at p, it will be tangent to the curve p, and its magnitude will be the speed of the particle at p. So it doesn't matter what direction it's going in, but however long that velocity vector is, that's called the speed, or that is the speed, because it doesn't have a direction. The magnitude of the velocity is the speed. Because remember that speed doesn't give a direction. So it doesn't matter if it's going forwards or backwards. It just matters how fast it's going. So it could be going 5 miles an hour forward, or it could be going 5 miles an hour backward, but it's still going, the speed is still 5 miles per hour. So the magnitude, do you know what that word magnitude is? Does that sound familiar from physics? Yeah, so magnitude is a distance, and direction tells you where that distance is going and what direction that distance is going in. So velocity is both of those things together. Velocity is distance and magnitude, whereas speed is just the magnitude. So it doesn't matter where it's going, it just matters how far it went, or how fast it's going, I should say. Okay, so it says the acceleration vector A is the derivative of the velocity vector, just like back in regular calculus as well. So you have this formula, which is the second derivative of x with respect to t and the second derivative of y with respect to t to find the acceleration vector. And its magnitude is the vector's length. So again, same thing with that Pythagorean theorem that you just square rooted to find the length of the magnitude, or the length of the acceleration. So they use r for position, they use v for velocity, and they use a for acceleration. All right, you guys ready to try this example? All right, so we're going to look at this example here, and there are 5 parts to it. So this kind of, usually when examples have 5 parts to them, they make really good free response questions. So this is probably something you would see on a free response question, or a free response test, I should say. So there's the question. It says a particle moves according to those 2 equations. So those are 2 parametric equations that were given, 3 cosine t and 2 sine t for y. It says find a single equation in x and y for the path of the particle and sketch the curve. So that's back to like parametric stuff. So why don't you guys take a minute and practice that. So practice eliminating the parameter and sketching the curve. So if I can move this up. All right, so for the velocity vectors, the velocity vector is just, well, let's start it with the position vector. All right, so the position vector would be r. And what should go here? Just x, actually. It's just x comma y. So x is 3 cosine t, because this is just the position, and then y would be 2 sine t. Then v is the velocity vector, so it's dx dt comma dy dt. So what's the derivative of 3 cosine t? Perfect. And what's the derivative of 2 sine t? 2 cosine t. And then the acceleration vector, what's the derivative of the velocity? Perfect. And? Good. The last part of that question says, show that a equals negative r at all times, and notice that it's true that this equals negative r at all times. So it's true that in this specific problem that the acceleration vector is exactly the same as the position vector, just in the opposite direction. So remember how I was talking to you guys earlier about when we drew that ellipse, and I showed you that if you start with the point for the position vector at the origin, and you can trace it out to different points on the ellipse depending on what time it is, or what t equals, I should say, the acceleration vector goes straight back to the origin again. So it's literally the exact same length as the line, it's just that it goes straight back to the origin. So it's the very opposite of the position vector. Essentially what that means is that the acceleration is always directed back at the origin. So as you're going around the ellipse, it just goes right back to the origin again. That's usually true of ellipses because do you guys know what centrifugal force is? Like if you take a bucket of water and you can like spin it and the water won't fall out. All right, that's essentially what centrifugal force is because the acceleration is always coming back to wherever you're holding the string. That it doesn't ever fall out because of the force, but it's more than you need to know. But essentially that's what it means, is that the acceleration goes back to the middle.
We did a lab on that.
Yeah.
Yeah.
Mm-hmm. All right, good. Let's look at part C.
That class all year.
Part C says find R, V, and A when t equals pi over 6 and when t equals pi, and then draw them on the sketch. So I think you guys could probably do that. All you have to do is for R, V, and A, plug in t equals pi over 6 and then figure out what the vectors would be, and then plug in t equals pi and figure out what the vectors would be. So I'll let you guys spend a minute doing that. So these are the values, and then it also says to draw the velocity vector, or draw all the vectors, I should say. So I'll do them in different colors so you guys can see them. So for the position vectors, here's the position vector for pi over 6. Well, it should actually go all the way out there, but you get the point. All right, so that's the position vector for pi over 6. This is the position vector for pi. In blue, this is the velocity vector for pi over 6. It goes kind of like this. And I'm not going to be perfect because, whatchamacallit, I don't have exact measurements on here, but essentially in the horizontal direction, you go negative 3 pi over 2, and in the vertical direction, you go up root 3. So negative 3 over 2 is negative 1/2, so that puts me back to about right, I don't know, like here. And then up root 3 puts me about, I don't know, something like that. Again, it's not perfect, but you guys get the point. It should be tangent at that point, and then something like that. For the velocity vector, it doesn't go anywhere horizontally, so the 0 component for that means that it doesn't go anywhere horizontally. The negative 2 just means that it goes down 2. So the velocity vector here goes something like that. And then in purple, I'll draw the acceleration vector. And remember, for this specific one, it goes back to the origin again. So the acceleration vector goes straight back to here for pi over 6 and straight back to here for pi. So those are what all the component vectors look like.
So when we want to draw the velocity, we start from the point that we ended at. But we want to do the acceleration, we start from the same point of the position.
They all start, okay, so the only one that doesn't start from the position is the position function. So the red one, essentially the red vector takes you to point P, then the velocity goes out from there, and actually the purple one starts here as well. So both the velocity and acceleration start from this point, it's just the acceleration goes back to the origin again. Yeah. Alright, we good on this piece of it? I don't want to skip over it.
Why doesn't the acceleration start from the velocity?
Why doesn't the acceleration start from the end of the velocity? Because the point that we're looking at is actually on, if I can draw it in green, the point that we're looking at is this point here. So it's an actual object that we're looking at, is whatever point that is on the graph. So the velocity is going that way as it's going around the circle, but the acceleration is being pushed back to, so the acceleration isn't at the tip of the velocity vector. The velocity vector is just showing you what direction it's going in and how fast it's going that way. The acceleration vector is still that same point that we're talking about, so it's within that point the acceleration is being pulled back to the middle again. Yeah.
So acceleration will always have the same basically vector coordinates.
Not necessarily. In this problem, yes, but that's only because this problem is an ellipse.
Okay.
I think with circles it would happen with, like when they go back on themselves, it'll happen. If it's like a parabola, that wouldn't necessarily happen.
Okay.
Yeah, it's just that all the power, all the acceleration is being forced back to the center of the ellipse and of the circle, that's why it happens in these shapes.
Okay.
Yeah. The next part of it says, find the speed of the particle. So remember that the speed of the particle is the magnitude of the velocity. So we have that formula that looked like the Pythagorean theorem. So to find the speed of the particle and the magnitude of its acceleration at each instance in C. So at pi over 6 and at pi. So go ahead and use those two formulas to find the speed and velocity, the speed and acceleration, magnitude of acceleration at those 2 points.